Hello, welcome back to Electrochemical Engineering. Today I'm going to talk about electrodeposition again, and particularly focus on current distributions that can be non-uniform in an electrochemical cell. Here's a simulation from COMSOL of depositing copper into a via, a trench in a semiconductor circuit. The electrolyte resistance to the corners of the trench is smaller than depositing at the bottom. This leads with time to buildup of copper here at the edges and the top relative to the interior of the trench. Thus, you have a non-uniform thickness of copper. These types of issues can be solved through the addition of additives to the electrodeposition solution. Here's another nice example of what can be simulated in COMSOL, showing the deposition to a PCB board, a printed circuit board of copper, modeled based on the resistances of the various components of the cell, showing both the thickness of the deposit here at the bottom here and the electric field lines that yield those thicknesses in the electrolyte. So usually we want a uniform electrodeposition. Not always, but usually. What might make electrodeposition non-uniform over a macroscopic scale? Why don't you pause your video and take a moment and think about why might deposition become non-uniform? Well, here's one example. Imagine you have an anode and a cathode. The edges of the cell are an insulator, an electronic insulator, and an ionic insulator, like plastic or glass. You are driving a current from the anode to the cathode. So there are positive charges depositing at the cathode, making neutral metal species. If this insulator is placed right against the edge of the cathode and the anode, your electric field lines are perfectly perpendicular to the plane of the anode and the plane of the cathode. In this case, the resistance for any ion moving, no matter where it's moving in the cell, is the same, and you get a uniform deposition. Now imagine you have edges. The edges of your cathode will have more electrolyte around them that they can utilize to transport current. And so they will actually have a lower resistance of electrolyte to move ions from the anode to that part of the cathode compared to the material in the center of the cell. Thus, you'll get a non-uniform deposition, and this is known as an edge effect. Here's another example. Imagine your cathode is tilted such that the current flow is longer on one side than the other. That also will lead to a non-uniform deposition, as one side of the cell has a shorter distance for the ions to travel than the other. We'll handle some of these quantitatively in this lecture. First, let's discuss the Wagner number. The Wagner number is something that Fuller and Harb introduced in Chapter 4, and that we'll cover briefly here. The Wagner number is defined as the ratio of the charge transfer resistance for a process to the ohmic resistance of the process. The ohmic resistance is simply the length divided by the area divided by the conductivity. The charge transfer resistance can be written very simply as the differential of the overpotential with respect to current. How much voltage does it take to increase the current? This is the same definition as in Ohm's law, V equals IR, where R equals dV di. This one is normalized to the area of the cell. If we recall our Butler-Volmer equation, we can write the current in terms of the exchange current density, the overpotential, and the transfer coefficients. We can take two approximations. We can assume that we have Tafel kinetics. Tafel kinetics are when you're far from equilibrium, and you have a large driving force, so you can ignore one of the terms in the equation. For example, we could ignore the left term, the anodic branch, since we're doing a cathodic electrodeposition. Then you can evaluate that derivative and get this for the form of the Wagner number. We'll come back to that in a moment. We can also take linear kinetics, which is where we linearize both these terms to make I as a function of I naught and the two transfer coefficients. We get rid of the exponents, and that approximation is good near equilibrium. Remember, the total Butler-Volmer expression gives curves that look like this, or if you're close to equilibrium, it's approximately a straight line. Now we can think about the Wagner number physically. If we're ohmically limited by the electrolyte, i.e. this is the ohmic resistance of the electrolyte, this resistance is much larger than these two resistances. In this case, we'll get a very non-uniform deposition because the resistance of getting charge from the anode to the cathode, where it can electrodeposit, is much smaller on the right side than it is on the left side. But imagine another situation where the activation resistances, the charge transfer resistances, those are large. In that case, the ohmic resistance is small, so it doesn't really matter that it needs to travel farther here than here. You'll get a uniform deposition no matter where you are on the cell. And that's just because the variation of ohmic resistance is unimportant due to the fact that the kinetic resistance is dominating the response of the circuit. There are standardized experimental devices for examining the current distribution. One is called the Hull cell. Now you can take advantage of the fact that here the distance is smaller than here, which leads to a continuous variation of the overpotential as a function of distance across this cell. Here the overpotential will be large because you're not spending very much free energy driving transport through the electrolyte. Here the overpotential will be small. So you can essentially do a single experiment which has continuous variation in current density and ohmic drop or overpotential, how much of your voltage that you're applying gets spent driving the reaction, across this device. So this is very useful for optimizing electrodeposition. You'll get some sample that has some variation in coding. You can go and look at the composition as a function of position if you're interested in that, or look at it with an optical microscope to assess the morphology, and then work out what's the best current density and overpotential condition to run your electrodeposition in. Another type of cell that's quite often used is called a Herring-Bloom cell, and it allows for something called the throwing power of a plating bath to be quantified. Here's how it works. You have an anode that you can move back and forth. So you can change X1 and X2 continuously, and you have two cathodes. You run your electrodeposition, and you calculate big K, which is the ratio of the two distances, and big B, which is the ratio of the two weights. If the solution resistance is small, the mass of these two electrodes, cathode 1 and cathode 2, after the electrodeposition will be the same. However, if the electrolyte is resistive, or if that resistance is significant compared to the charge transfer resistance at the electrode surface, then you'll have a non-uniform deposition. One of these cathodes, in this case cathode 2, will weigh more than cathode 1. And the throwing power here in percent is just then given by this expression. And you can see here when W1 equals W2, B goes to 1. If I plug B equals 1 here and simplify, I get 100% throwing power. This means the electrolyte can deposit far away from the anode with good uniformity. We should also briefly talk about side reactions. In water, the most common side reaction is hydrogen evolution, that is, making H2 from water. This leads to a loss in Faradaic efficiency. Remember, Faradaic efficiency of the fraction of the current that goes towards the intended process. But sometimes side reactions can be used to reduce the deposition rate at locations with highest overpotential, thus improving uniformity. For example, you could use a side reaction with an additive that improves uniformity in this way. Bubbles are also formed by hydrogen evolution, and that can actually increase the ohmic electrolyte resistance and cause further non-uniformities in your cell. But bubbles can also improve mixing. However, bubbles can also improve mixing, particularly at the boundary layer, the diffusion layer, thereby increasing mass transport. Here's an example of some current density as a function of overpotential here. You'll notice here the metal has faster kinetics initially, but at the higher overpotentials, hydrogen becomes to dominate the reaction. That's because there's lots of water to reduce. And that's because there's lots of water to reduce, but you can indeed run out of metal species to reduce on the surface. Now let's switch gears and talk about resistive substrates. So far we've only discussed resistance due to the electrolyte, but there are many examples where the potential drop in the substrate is important. So the overpotential is not constant with position. Some examples are chrome deposition onto plastics, metal deposition into microelectronics, where the microwires connecting all the circuit elements are small. For simplicity here, we're going to assume the conductivity of the substrate is smaller than that of the electrolyte. When both are very important, you'll need more complicated models. For example, if you have a Wagner number greater than 10, then the electric potential of the solution is essentially a constant everywhere at the electrolyte electrode boundary layer. This is because our ohmic for the solution is small. So you have a uniform electric potential at this electrolyte electrode boundary. On the left here, we have a current collector, which is where the electrons are coming from that reduce the ions to metal. The surface of the electrode is metallic, and it's typically a thin film. That's why it's resistive, and it's sitting on an insulator that can't conduct electric current. And the electric potential in the metal decreases from X equals L, the edge furthest from the current collector, to X equals 0. So you can see here that the difference between phi metal and phi solution is going to change with position. That's because phi solution is constant, while phi metal changes due to the resistance of this thin conductive film. Let's do this quantitatively, keeping this picture in our brain. We can define the change in the current in the metal, dI1, with respect to position as a function of the current flow between the solution and the metal, IN. This is going to be negative for a cathodic process because we're doing a reduction process, times the area, the interfacial area of the substrate per volume of metal. So this is very similar to what we did in porous electrode theory. Changes in the current through the electrode, through the metal film, have to go into interfacial current flow between the metal and the solution. We can define some boundary conditions. The current density, I1, equals the total current divided by the cross-sectional area at X equals 0. Remember, X equals 0 is right next to the current collector where all the electrochemical reaction has occurred. So at that point, all the current is flowing in the metal. I is the total current. I1 equals 0 at X equals L. X equals L is the point furthest from the current collector. And we can think about the current as being positive charges that are going onto our metal and transporting down its length. And as you move down the length of the thin film, more and more positive current builds up because there's more and more electrochemical reaction that thin film is carrying. ARS, again, is the cross-sectional area of the electrode. It's just its width times its thickness. Here's thickness. And width is going to be in this direction. It's a two-dimensional film with some thickness, delta. Now we can also write I1 in terms of the electric potential drop in the film. This is a form of Ohm's law. The current is just the conductivity of the metal for electrons times the gradient in electric potential, the electric field. We can recast this derivative, d phi 1 dx, in terms of a derivative in the overpotential. That's because phi 2 is constant, and the derivative in the overpotential, which is defined here, the difference between phi 1 and phi 2, is identical numerically to the derivative in phi 1, because phi 1 is the only thing that's changing as you go along the x direction here, back and forth. We can also rewrite the derivative of I1 with respect to x from over here, from our definition, in terms of a Tafel expression. So I've just plugged in for IN using this Tafel expression that is ignoring the reverse reaction. So this is only the cathodic branch of the full Butler-Volmer expression. Now we can take this expression and we can differentiate it again with respect to x. And you have to remember the chain rule. So the derivative of a function that's a composite function is the derivative of the outside function evaluated at the inside function times the derivative of the inside function with respect, in this case, to x. So we can do that here. Here is the outside function. When I take the derivative of an exponential, I just get an exponential back. And here's the derivative of the inside function, these two terms together. You notice the inside function, the only thing that depends on position is the overpotential. So that's where this expression comes from. I can recast this now by noticing that the middle term here is just the change in I1 with respect to x that we defined earlier using our TAFL expression. Now we can take this expression from the previous slide and we can define some dimensionless parameters like we normally do. We'll make I star the current in the metal divided by the total current density. Remember, these little i's are really current densities. And we'll make x star the position normalized to the total length of the electrode. And now we have a dimensionless differential equation here that can be solved. Notice this term out front of the differential. This term is related to the ratio of the substrate to kinetic resistance. Notice you have I and alpha C here on top. That's related to 1 over the kinetic resistance. And you have sigma, which is related to 1 over the substrate resistance. Remember, sigma is the conductivity, and that's related to 1 over resistivity. When this ratio is very small, the second derivative goes to 0, or the change in current with respect to position is constant. So what does it mean this ratio is very small? Well, what it means is the ratio of the substrate to kinetic resistance is small. So the kinetic resistance is much larger than the substrate resistance. And that is, of course, our situation when we had uniform current. If the substrate resistance is very small and the kinetic resistance dominates, that's similar to our previous situation where the potential drop in the substrate, in this case, is negligible. If the potential drop in the substrate is negligible because all of the resistive drop is across driving the kinetics, across the equivalent resistor of kinetics, that means that the deposition will be uniform because phi1 is not changing substantially with position. Remember, in order for the overpotential to change, since the solution potential is constant, phi1, the potential in the, but if it's a good conductor, if the resistance of electronic transport is small relative to how fast the kinetics need to go, then you'll have a uniform deposition. We can recast this in terms of the overall average current in the cell. So we can write I as just the average current times the width times the length of the cell. So remember, our cell is this thin film with some thin thickness delta, and we have a length and a width. So this is just the area of the surface where the electrodeposition is occurring. Now I'm going to take this term and I'm going to write the inverse of this term and call that chi. Chi is going to be, again, the ratio of the charge transfer to substrate resistance. We'll need to understand the value of chi, whether it's about 1, so they're both important, or whether one of them is dominating to predict how electrodeposition will occur. We'll work through some examples now in class. Now let's think about the relationship between WA, the Wagner number, and this chi value we just learned about. If WA and chi are both important relative to charge transfer, we need to consider also their ratio. So remember, for TAFL kinetics, we define the Wagner number as such. So we can take the ratio of chi to the Wagner number, and this is really then a ratio of the ohmic resistance in the electrolyte to the ohmic electric resistance in the substrate. Now, L in the Wagner number is related to the length of the electrolyte. L in the derivation of chi was related to the length of the electrode. Now, if these are similar in magnitude, we get this expression, where you see that the ratio of these two could be estimated by the thickness of my sample, the conductivity of the electrolyte, kappa is the conductivity of the electrolyte, sigma, the conductivity of the substrate, and L, the length, the characteristic length of the electrode and electrolyte. And that leads us to these 4 situations. If WA is much greater than 1 and chi is much greater than 1, the current density is uniform because charge transfer resistance dominates both these. But if WA is smaller than 1, the Wagner number is smaller than 1, and chi is bigger than 1, the resistive substrate is not important because chi is bigger than 1. The resistance of the charge transfer is much bigger than that of the substrate, so we could ignore that. And the current distribution is determined by the Wagner number. Remember, the Wagner number is how the deposit is affected by the electrolyte resistance. Now, conversely, if the Wagner number is much greater than 1 and chi is smaller than 1, the solution resistance is not important, and the current distribution is determined by chi. Chi being representative of the substrate resistance relative to the kinetic resistance of the electrodeposition. And then the most complex problem is when both are relevant, both the substrate and solution resistance are important, and you need to know WA, chi, and the ratio to estimate what you expect your deposit to look like. Let's go back to the case where WA is much greater than 1, so we can ignore the electrolyte resistance. And the current distribution is just due to the substrate resistance. So you can go through and solve the differential equation. And when you do that, you can get now a plot of I over I average as a function of the dimensionless distance. Remember, this was x star equals x over L. And what you see is when you have chi equals 0.1 or 1 over 10, the deposition is uniform everywhere. At chi equals 10, you have much more deposition next to the current collector. Remember, our current collector is on the left side at x star equals 0 than you do out here at the edge. Why is that? Well, it's very simple. Here is where you have the most driving force for the reaction because you haven't had to pay the price of moving the charge through the resistive substrate. So the deposition happens where the electrons can get to the easiest, or where it's easiest to get the current out. Here's an example from a nice paper that takes it one step further. You can see here a sketch of the flow of current through the electrolyte phase during deposition onto a resistive cathode. This is exactly what we've been talking about. Notice how the current focuses at the point close to the current collector. And there's a lot less current out here where the electrons have to move a large distance. This leads to a non-uniform electrodeposit. One of the things that's very nice in this paper they discuss, and what's interesting, as you deposit more and more and more material here, notice that you now have a thicker metal. So if this is a metal, say metal 2, and this is metal 1, you'll notice that metal 2 is getting thicker and thicker and thicker on the left-hand side. And what this works to do is it actually reduces the resistance of getting the electrons out here, or conversely think about moving the current from out here back into the current collector as positive charge flowing. And by reducing that resistance, eventually you'll get to the point where the current distribution is actually equal everywhere. And that's because you've actually increased the thickness, you can think about it, the thickness of your wire carrying the current at the bottom where it's carrying the most current. And so nature will work to make the current distribution uniform in this case. So that's all I have for you today. I'm looking forward to discussing this with you in class later.